Welcome back to the session. It's a great pleasure for me to introduce you the second speaker of today, which is Professor Irène Gijbels from the KU University of Leuven, and she is presenting us on dependencies in high dimension and in complex data structures. Thank you, Irène, for coming. The floor is yours.
Thank you very much. It's a great pleasure for me to be here in Padua. It's actually the first time. And actually, I'm coming from a very young university because in 3 years from now, I think we are celebrating on our 650th anniversary. So it's quite young university. I should also apologize for maybe the topic, because if you would have expected me to talk about smoothing, regression models, regularizations, which is one of the things I have been doing for decades, I'm not going to do that. I somehow jump a bit into deep water with this talk, and it's nothing which is really very deep. The original, actually, let's say the way how I got into this research was that I essentially was asking some questions, and I was surprised about the fact that the answers were not there. So it's very low level in some sense, but I hope you can still learn something from it. On the way, you will see some. I will talk about some results that I obtained with one of my former PhD students. And one of my current PhD students and collaborators, among others, at Charles University in Prague, in Czech Republic. And also at the very end, I will say something about work that I'm doing with Jose Ameyars Alonso from the University of Santiago in Spain, Santiago de Compostela in Spain. Okay, it's not, okay. I'll just start with like a kind of toy example, because I will, on the way, talk a little bit about that more. So it's a data set about environmental measurements, and there were about 219 variables. The data is available on this website mentioned here, and it basically measures all kinds of pollutants, I would say. And they are measured for thousands of locations across the US. I will, and basically the variables were like categorized into 5 domains: air, water, land, built, and socio-demographic. I will restrict to 3 variables in 3 domains here, and I will also restrict to variables which essentially have not too many ties in the observations, which means that in the examples that I will show, I will consider basically 9 variables out of the air domain. They're listed here, but don't start reading them. Water, also 9 variables. Land, 4 variables. And if you combine them, there are 22 variables. Okay. Now, and essentially, very simple. I would like to find out association between these variables, right? Very simple. Now, what is always done, essentially, well, if I would have to do that, and I will show you a picture in a moment, I mean, a first-year student would immediately maybe start calculating Pearson's correlation coefficients if I have 2 variables, right? That's what somebody would do. But of course, we know you only measure like linear dependence or linear association. And we know that when x1, x2 has a bivariate normal distribution, then essentially you have this characterization, this equivalence with this parameter rho. Of course, you need finite variance for that. And so we want to stick away a bit of these restrictions that I mentioned here. And then people came up way back in the previous century with other association measures, more robust, non-parametric, if you want to prefer that name, Spearman's rho, Candle-Stowe, etc. Okay, Candle-Stowe, the bivariate version. So it measures of strength, of course, and everybody knows this, right? I hope. So you have an independent, independent copy y1, y2 of x1, y2, and so essentially what Candle-Stowe does is measuring the probability of concordance between these 2 pairs minus probability of discordance. Spearman's rho, you have a similar kind of definition, let me just immediately go to this expression. Spearman's rho is essentially Pearson's correlation coefficients, but not applied on the original data, but on the ranked data, right? So what's coming in here is like, if X1 has cumulative distribution function F1, this is the uniformized marginal, if I may call it like that, and this is the uniformized second margin, right? It's like the ranks if you think in terms of data. There are many other association measures in the bivariate case, Gini's index, Bloomquist beta, etc. So there are many more. What about, so this is the strength of the dependence. What about the dependent structure? How can you basically measure that? Of course, you can come up with regression models and start working with that. But you can also go back to a very fundamental theorem by Sklar, which says that there exists a copula, which is a function defined on the unit square, taking values in 0, 1, and which is essentially the function that couples the joint distribution function between x1 and x2 with this marginals. And this function is unique as soon as these marginals are continuous, which I will assume throughout the rest of the talk. And so this copula function fully describes the dependent structure. And another important point to note is that it's actually the joint distribution function of these uniformized margins, right? Now, the good thing is, and the nice thing is that these association measures I was talking to you about, they all are like kind of known functionals of the bivariate copula. Now, Candle-Stowe, you can express it this way. This is, by the way, results which are there for ages already, for decades in the literature. And so important is to realize that they all are like known functionals of the bivariate copula. And I just added index 2 there to indicate that this is the bivariate case. And so this means that if you would like to estimate these, it's quite simple. Estimate the bivariate copula from the data, plug it into this known functional, and you get your estimation, for example, for Spearman's rho, Candle-Stowe, whatever association measures that you consider. So this is the heat map, a heat map which basically shows empirical pairwise Spearman's rho values for these 22 variables which I considered, and this is pairwise. So I'm only looking like 2 variables at a time. And so the bluish color is positive values of Spearman's rho, and the red colors are like negative values of Spearman's rho. And essentially what you see is that, well, there are many things you can start looking at from this heat map. And you basically see that all the variables in this air domain are positively associated to each other. The same for the 4 variables in the land area. And if you look at associations, for example, you see that there are 3 variables in the water area, sulfate, mercury, and chloride, that all have like a positive association with each of the variables in that air domain. But this is looking pairwise. And when I see this, I always wonder, well, you only look pairwise. What happens by looking at higher order dimensions? So this was essentially my question that I had years ago. I mean, it's a very simple question. So let me come to multivariate association measures, because this is something you would expect is by now standard, right? And in fact, it turned out it's not. There is a lot to be learned about this, I think. Maybe not very interesting, and maybe not something that is going to change the world, but at least something which gives us a kind of basic understanding of what's going on. Okay, so what now if I have, instead of a bivariate vector, I have a d-dimensional vector, and I would like to measure the association between the d components. Which properties am I expecting from such an association measure? That's the first question I would ask, and I asked myself, what happens if I add an independent component to that vector? What happens if I just add a component which is already there? What happens if I add an arbitrary but fixed number of components? What happens with this association in the vector? I think these are questions I would expect the answers are there. So let me try to come to how you could define multivariate association measures, and you will see that there is a lot of things which are available in the literature. Actually, an easy way for me to do it is by just starting again from Clark's theorem, because you have the multivariate version is there, which then says that there is a copula function with now the index d, that because it's d-dimensional, living on the d-dimensional unit cube. And it couples again the joint distribution function between the components x1, xd with the marginals. And so again, CD, the copula, is actually the joint cumulative distribution function of these uniformized marginals. Okay, what about multivariate association measures? If I follow the same stream as with the bivariate association measures, that essentially we saw that it's a functional of the copula, the bivariate copula. So you do the same here. You're searching for a function kappa d, which basically assigns to each copula a strength of the dependence. And you would like to ask the question, which properties do you expect that this multivariate association measure has? Well, there are some lists in the literature, but there is for sure not a kind of conventional wish list of properties that you would like to have. And before I show you the list that we were using, let me introduce some notions. If you have copula CD, you have a survival function of that, which is like the usual survival function that you find in survival analysis. You also have the notion of survival copula, and the survival copula is actually the copula of 1 minus u. Yeah, and it's linked to the survival function that evaluated at different points. There is also a kind of ordering notion that you might have, which says that if you have two copulas, then they are ordered in this concordance ordering sense. If when AD is less or equal to BD for each argument, and actually the same holds true for the survival function, then you have this ordering. Actually, in 2 dimensions, this is not needed because it follows from the first part. Another thing that I need in order to make you understand a bit things is that there are notions of reflections in this d-dimensional unit cube, meaning that if reflection is just a mapping of u on v, where essentially some of the arguments of u just stay the same, and some of them might flip inside this unit cube, right? And there will be a notation like the set of all reflections coming up. And in fact, if you take a reflection, and if I give you a copula CD, then actually that reflection together with the copula creates a new copula. Let me just give you an example. If I take as a reflection of all components, so I'm flipping actually each of the arguments, which essentially means that the copula, if I have the copula CD of these components, I would look at the copula of the same vector, but with the minus sign. Now, if I ask you the question, would you, if you have to have an association measure for this and for this, what do you think? They should be the same, right? So one of the things in the wish list, which don't read it. One of the things in the wish list is actually this duality property, which is exactly saying what I was mentioning on the previous slide. I mean, that's what you would like to have, right? Among other things, so don't read all the things, but there is a kind of ordering which you would expect, which is a logical ordering of any kind of reasonable association measure. And there is something which I would like to draw your attention to. By the way, for this list of axioms or desirable properties for the bivariate case goes back more than half a century. And the list, in some sense, desirable properties for multivariate association measures, not the list that I'm showing you, but you find some kind of listing of desirable properties in the literature. Let me draw you this attention to this A8. This A8 is the following. Suppose I have a vector of D components and I add an independent one. What do you expect of an association measure to do? Well, if there was already no association here, you expect that it stays like that, right? If there was like a positive association and you add an independent component, you expect it to stay positive but shrink. If it was negative, you expect it to become a bit less negative. I mean, that seems logical, right? So we added A8 to your wish list, if you want to say it like that. So let me now go to how do you get to multivariate association measures? I mean, this is a very basic question. And in fact, if I just brutally group the approaches in two different categories, essentially what you find is like a pairwise approach, which is essentially people look at all kinds of pairs and look at association measures for that. And then you add up all these pairwise association measures, you normalize or you standardize, and you get a multivariate measure. Another approach is via the Coppola approach, and I will comment on both. So let me give you one slide on the pairwise approach. So suppose you give me a good bivariate association measures, and there are many that you can take off the shelf. And I basically look at each pair of components in my vector. I calculate that association measure, I add them up, and I just properly divide by the number of pairs that you have in your vector. Is that a good thing to do? Well, the proposition that I show you here, don't read it, I will tell you what it says. Essentially says that if you start from a good bivariate association measure, which basically fulfills your 8 properties or desirable properties, the same will hold for your multivariate pairwise association measure. Of course, what you always will have is that if all 2 components have association measure 0, your multivariate measure will always be 0, of course, because it misses actually any kind of higher order dependence. Which is the reason why we don't like it too much, and which is the reason, in some sense, why I was wondering, why is everybody always looking in applications only at pairwise associations? Because you might miss quite something. Now let's look at what's around in the literature based on the Coppola approach. For the Coppola approach, and I will focus mainly on 3 of these bivariate association measures, just to try to pass the message to you what is happening with there when people are starting to do this generalization. And some of these things are really old. I mean, compared to me, they are maybe young, but. So if I start from multivariate Spearman's row, this is the expression. And remember that U1 and U2 are uniformly distributed on 0, 1. So I know what the variance is. I know what the joint distribution is because that's the Coppola. And actually you can express this in a complicated way with Coppolas. What's coming up there? Well, that's the Coppola C2, which is the joint distribution function of U1, U2. What else that comes up is the independence Coppola. So the dependent structure you would have if there is independence. And also the comonotonicity Coppola, which is the Frechet upper bound, which means any bivariate Coppola is actually bounded by that one. So it's like the kind of strongest assumption that you can, dependence that you can have. So this is actually the bivariate Spearman's row written in a complicated way, but in a complicated way which immediately allows you to basically go to D dimensions. Because you just replace C2 by CD, you replace the independent Coppola in 2 dimensions with the one in D dimensions. This one, similarly, in D dimensions, the definition is immediately there, and that gives you the first generalization, which dates back more than 40 years, right? And you have a proper normalization, standardization, which is there. Now, there is another version around of the multivariate Spearman's row. And how do you come to that? Well, you do in the bivariate case, you do a partial integration, and you come to an expression which is essentially something like an average distance between your bivariate dependent structure and the independent Coppola structure. And if you from here do the same, you replace the bivariate versions by multivariate versions, you get to another version of another multivariate generalization of Spearman's row. They're not the same. They are the same in a bivariate case, but not in the multivariate case. Which then, when I saw this for the first time, I thought, okay, I have two measures for something. What should I basically choose? And essentially, so we started looking into these desirable properties, and some of the things were there in the literature. For example, both measures basically, you cannot choose between them because they both equally satisfy these properties A1 to A7, which I listed, not this duality axiom, right, where you have that the association of x1, xd is the same as minus x1 minus xd. They don't satisfy that. And they satisfy actually the independence type of property that was, we showed this a year ago. Okay, multivariate Campbell stone. There the story is easy. Why? Because there is only one multivariate version around in the literature, which is easily obtained from the expression in the bivariate case. Replace this by bivariate coplas and you get to this. And actually that one satisfied all the desirable properties that you might list. Maybe you want to add some more desirable properties, but that is what it is. Gini's gamma, and that's the last one I mentioned. Actually, there the story is again different. Because if you look at Gini's gamma in the bivariate case, it has this expression. You have to work a bit in order to get it. What is coming up there? C2, but also the Frechet upper bound copula and the Frechet lower bound copula and their survival versions. But again, the generalization from this is in some sense quite straightforward. The only thing you have to be aware of is that if you generalize the Frechet lower bound to more dimensions, it's no longer a copula, right? But you have an expression, you have things which are around. But there is another version around of multivariate generalization of Gini's gamma, which is this one, and I'm not explaining where it comes from, but you can look at the papers for that. You get to this, where these survival copulas are coming in, where these reflections are coming in. And in fact, our first question was, can I compare the two? Which one of the two should I use? If I want to use a multivariate Gini's gamma, which one should I use? That was my question years ago. In fact, one of the important things to mention is that there is a d-dimensional integral here. And what we managed to show essentially is that using properties of these reflections and things like that, is that you can reduce this to a one-dimensional integral, which is already something that, you know, I'm much more in favor if you have to start calculating things, ending up with that. So that's one thing, but then still remains the question, what about these two generalizations of multivariate generalizations of Gini's gamma? Which one of the two is satisfying my wish list things? And there again, something very surprising came out of it, because the first generalization actually only satisfies the three first properties, does not satisfy this duality property, nor does it satisfy this AA property. We do have counterexamples for that. Whereas the second one, which is also the simpler one, actually satisfies all of them. So I think the message that I would like to convey to you, and I told you it's very basic things, is that essentially passing from bivariate to multivariate association measures, it's not like a cooking recipe. And what you get, you should investigate and know what properties they basically have. Now, I'm not going to tell you about the properties that we found in the sense of when you add a number of components, what happens with the growth of that association measures, because I would like to know it, right? If you want to look at more and more variables, then try to have an idea of what happens with this evolution of this association measures. I'm not going to give you the results that we found on that. Because they're actually sparse. We don't have that many results, which was shocking to me also when I looked at it. And I will immediately, in some sense, go to a kind of like, call it an artificial setting, but the setting where we let the dimension go to infinity. And let's look what happens with that. Now, of course, when you take a vector of d components and you let the dimension grow to infinity, of course, if your dimension grows, your dependent structure can change. So I can only study that, of course, when the dependent structure stays the same, because otherwise it doesn't make any sense. Which means that you can't study that in full generality, but you can study that in settings where essentially you can control the dependent structure staying the same when you increase the dimension. And there are two settings which we were able to obtain some results, not only we, but also in the literature. That is by looking at Archimedean coplus and meta-elliptical coplus. And Archimedean coplus, just in a nutshell, are coplus that are generated by one single function psi, which is a function on 0 infinity, and then you basically apply psi to the inverse in each of the arguments. So it's a very special class, and there are many functions of psi which are around. Okay, these are the results. And maybe look first of all at this result, which is not by us, but it's in a paper which was published 7 years ago. Basically, it says that if you measure association measures with Kennel-Stahl, and you do this, and you are in the Archimedean coplus setting, you will always end up with 0 as an association measure if the dimension increases. Okay. The same happens with Gini's gamma in increasing dimensions, and that is something that we just proved. The same is not happening. Well, I'm not sure what I should be a bit more careful what I say. I think the same is not happening with these two, versions of Spearman's rho. Why do I say I think it's not happening? Because this result was actually in that paper, saying that the limit when d goes to infinity is a number between 0 and 1. And effectively, we do have examples where we study by simulations what happens when you increase the dimension and it doesn't go to 0. I mean, all this is like kind of a bit shocking to me in some sense. Meta-elliptical coplus. So what are meta-elliptical coplus? Essentially, think of a elliptical distribution, but now in the copula world, right? So you have elliptical contours. Luckily, some work has been done there in terms of multivariate association measures, but little. There are results on the multivariate Kennel-Tau expression, which essentially it was shown by Christian Geneste and collaborators that all meta-elliptical coplus with the same correlation structure do have the same value of multivariate Kennel-Tau. Okay, that I'm expecting that. And actually you do have an expression of that in the sense that you see this is the dimension popping in, and you have the probability that a normally distributed random variable with mean 0 and correlation matrix R, actually that probability is coming in. And I had the same question, what happens when D increases? Effectively, the answer to that question is we only have partial answers to this question. And the partial answers are actually for two very specific correlation structures. And we have no idea what happens with other correlation structures. What correlation structures do we know the answers? Well, if you have that the elements of your matrix are of that product form, or that includes the situation that you have equally correlated correlation matrix, so the most simplest setting that you would think of. And another type of correlation matrix is a banded type. So suppose you have a three-dimensional banded type of correlation matrix, so the diagonal is 1, and then the diagonals above that and beneath that are different from 0, and all the other ones are 0. And for these two cases, we were able to show, under some additional assumption on this first correlation structure, that Kennel-Stahl goes to 0. The question is, what happens with other correlation structure? No idea. I mean, no idea about that. Okay, let me say something about non-parametric estimation, because this is like coming home, right? Talking about non-parametric estimation. How am I going to estimate all these multivariate association measures? I want to have like not only an estimation, but I want to have like standard errors, for example. Well, that's fairly easy with what is there now in the literature. In the sense that, remember that CD is a joint distribution function of these uniformized marginals. But if these marginals are not known, I don't have observations on these uniformized marginals. I don't know the coplus structure in a fully non-parametric setting. So what you have to do is you first start estimating these unknown marginal distribution functions. That's easy, the empirical distribution function. Except that we are not dividing by 1 over n, but by 1 over n plus 1. Why? Because we want to stay away from 0 and 1. That's the only reason. Once you have that, okay, estimating like you have like kind of pseudo observations of these, and you can construct the empirical version of CD, which is the empirical copula, which goes back to the Gijbels in 1975 or something like that. So which is this, right? And of course, if you have the survival function coming up, that's equally well. And if your kappa d, I dropped the d here for simplicity, is a known functional of CD, you basically replace CD by the empirical estimator, or even the C bar, which when it's appearing, and you can basically get to an estimator quite easily. And luckily, there are results on uniform convergence of empirical copula processes, not only for the copula CD, but also for the survival function, also for the survival copula. You need that. And people have been working hard in order to get to weak convergence results for those under the weakest possible, well, or under a set of conditions which is as weak as possible that we have now. And actually, you even have joint weak convergence of the empirical copula process and the empirical survival copula process, which you need in order to say something about non-parametric estimators of these multivariate association measures. So, like, for example, if you want to know something about Spearman's rho, look at this paper. For non-parametric estimation of Campbell's tau, there is this work by Genest and co-authors. And for, yeah, and I should tell you, we have, I mean, things that are available based on the results which I showed you on the previous slide. If I want to say it in a very simple way, it's not that simple, but you get to an asymptotic normality result for which you have an expression even for the asymptotic variance. Similarly, for genius gamma, the only version which I think we should work with, not the other one, we do have that also with an expression for the asymptotic variance. And you can essentially use bootstrap techniques in order to estimate a standard error, or you can even rely on this asymptotic results and rely on new statistic theory, which is behind that. So it's fairly easy to do. And I think I'll skip that slide. Let me come back to the 22 variables, right? So what people standardly would do is like, do this. You calculate the pairwise Spearman's rho, Campbell's tau, genius gamma, whatever is your favorite. And I'm looking actually here at a kind of combination, a cluster of variables, which are these 9 air variables, plus these 3 water variables, which were positively related. I take them as a cluster. There are reasons behind that, and you basically see if you use the pairwise measures, these are the numbers that you get with the standard deviations. And this is when you look at the multivariate associations. And I'm just raising for myself the questions, we should actually not only look at the pairwise associations, but go beyond that. That's the message that I want to say. And the other message that I want to say is this is possible. Okay, let me move on because the story is not finished. Because I kept quiet about extreme events. Now, extreme events, we know them every day. Luckily, it's nice weather here now, but we have had, like, in Belgium, very unusual temperatures by not seeing 1 drop of rain for more than 3 months. We have rain now, so we are very happy. But you have, like, high temperatures. You have, like, when the rain comes, it's like not normal, the amount of rain that you get. When the wind is blowing, it's like not normal. So there is this kind of extreme events. And you want to look at what happens when the temperature rises, what happens with the amount of rain, for example. So you want to look at a kind of tail dependency. Now, in a bivariate setting, this is easy. But in a multivariate setting, again, the same story I could repeat, which I'm not going to do. But it's the same kind of thing. So in a bivariate setting, this is all very well known in the sense that if you have, if you look at the upper tail coefficient, you look at one variable which exceeds a certain threshold. What is then the probability that the other one also exceeds that certain threshold? And that threshold you want to push to the limits, right? You want to look in the tails. Now that's a function of the bivariate copula. It's the same story as before, except that now there is this limit coming in, which makes it more annoying. Now in the multivariate setting, when I started looking at that, and I'm not a specialist in this, let me say that very clearly, you see different versions. And what are the different versions that are around? Actually, the version that is used, according to me, most in the applications is this one. So that's one where you basically condition on, compare with this if you want, that you condition on the maximum of these uniformized observations. If that exceeds a certain threshold, you're looking what happens with the minimum of that. But you select them, right? You make that choice. And the thing is that, and again, you can express that in terms of the co-plus. It's the same story. The thing is that if you would look at what this gives in 2 dimensions, it doesn't give you back these. It gives you a relation to them. So it measures a kind of other tail dependence. Another version that is around, but which is practically less feasible, I think, is that you essentially would choose from your D variables a subset on which you condition, and then the other ones would come in the probability in front. But then the question is, of course, which subset should I look at? Should I look at the temperature and the amount of rain compared with the direction of the wind speed, for example? What should I bring in there? That's actually a practical question. And so the choice of the subset is not such an obvious thing. Also not I haven't seen this dealt with in applications. The good thing is that if you go back to the bivariate case, it goes back to the ones that we are always using. And there are others that I'm not describing. So in some sense, what I want to say is that, and that's what we also did, we essentially looked at desirable properties for these tail coefficients and looked at those that are around in the literature and checked, are they basically like satisfying or desirable properties, as we did in the other case. Another thing that I should mention is that when you talk about extreme events, people like to work with extreme copulas. And an extreme copula, as an Archimedean copula, is expressed in terms of a generator, which is called Peakin's dependence function. And there is quite a lot known about that. So you could try to study what's happening with that, and you can basically, in that context, also present new tail coefficient measures, which you could also look at a kind of pairwise approach, which we did. We looked at properties when you add an independent component, what happens. It's all very, for me, this was like so basic. And so I was so surprised that this was not available in the literature. And we looked at basically how to ask these non-parametrically. And even that is something that is like not really studied. Estimation of the Peakin's dependence function, yes, but not the estimation of the tail coefficient function, which is not the same. Let me give you one slide about smoothing. I mean, I should do this, right? Which is the Franz lower tail coefficient is that, right? So how would you estimate that? We know how to estimate a copula. That's the empirical d-variate distribution function based on the pseudo observations. The only thing is I dropped this limit, right? And you replace u by a sequence which goes to 0. If you want to show consistency, you see that the sequence has to go to 0, but not too fast. And essentially, you know, this quantity plays a role of the number of extreme observations. But how to choose it in practice? I mean, I was surprised to see that even for that, there were no results available. And basically what we did is, by showing consistency, by looking at the bias, by looking at the variance, what kind of thing we could come up in order to choose that smoothing parameter, if I may call it like that. But I was surprised to see that this is not there. Where did we use these kind of results? And I don't know how much time I still have. 5 minutes. Oh, I will make it, I think. No, don't read this slide. I'm not a good example of, if you don't have to read it, I shouldn't essentially include it, right? But okay, I take that message. Essentially, what we did use these things for, these multivariate association measures and these multivariate tail coefficients, we use this in variable clustering. And I should say that Fabrizio was among the first people who basically starting showing how to do that. And we basically, yeah, just followed what Fabrizio was doing. So in a sense, what you basically do is the following. So you want to cluster variables, right? So you have like, think of xd to x1, x1 to xd as d objects for which you have n observations, right? And you want to somehow cluster these variables, the variables, right? What you do is you start by putting each variable in one cluster separately, and then you start merging variables into a cluster. How are you doing that? Well, you are using, well, you are merging them, and you calculate a bivariate similarity measure, an association measure, and then you get to a dissimilarity measure, for example, by taking 1 minus the square root of that, or square root of 1 minus that squared. So you change from an association measure or a similarity measure to a dissimilarity measure. And what you essentially do is that you start merging clusters which are like too similar, or for which the dissimilarity measure in somehow is too low. That's what you do. Now, that actually goes further than comparing like two real valued values, because you can also do this in multivariate setting, in the sense that if you have already two pairs of clusters, you want to basically calculate their dissimilarity, and you want to merge them in some sense when you want to put two clusters together in some sense which have the smallest dissimilarity measure, or which are too similar, put them together, right? The similarity measure that was used by Fabrizio, if I'm not mistaken, is actually the multivariate Candle's tau, but instead of using that, you take 1 minus that, so you swap to this similarity. If we did this, well, we did this on our toy example for extreme observations of pollutants. Yeah, and I'll just show you the picture. So essentially, there were these 22 variables. We did this variable clustering approach using tail coefficients, using Fran's tail dependence coefficient, trying to find clusters of pollutants which basically both, you know, like go to the extremes together, if I may say it like that. And sometimes you find like clusters which are quite to be expected, like lead, zinc, and copper you find together. Another cluster, which is this one, magnesium, potassium, sodium, and chloride, you find together. So these are essentially in this water area. But you also find herbicides and ammonium together, which are from two different domains. But it's not so surprising, because actually these herbicides are based, many of them are based on ammonium. So so you do find some kind of surprises there. And so you see that these tail coefficients, they basically can learn you something when you go to clustering applications. Now, what's up next there for questions, for me at least in this area, that is that you do not only want to compare two clusters, you want to compare more than two clusters, three clusters, etc. You want to step away from this pairwise comparison, even if it's between clusters, which basically means that you would need association measures, not between only two random vectors, but between k random vectors. And there is actually very little done in that setting, or not enough done. And some of the recent approaches that I just would like to mention to you is that these two people started, Gilles Mordaunt and Johan Segers, they started using optimal transport IDs for measuring association between two random vectors. Now, we looked into that, and you can essentially easily, you know, generalize this for k random variables. Well, easily is not the word, but you can do that. The difficult thing is measuring, you know, really, if you want to go beyond like a normal distribution, it's not easy to calculate. That's one thing. What we found more promising is working with phi divergences, meaning that borrow actually knowledge which is there in information theory, like mutual information these kind of things are actually quite easy to handle, and you can actually compute them more easily. Well, I should be careful with how I say it now, because we are somehow in the stage of doing this, that you can basically prove a wish list of properties that you want your phi divergences to satisfy. But there are still many questions that are there, and let me try to finish with well, something that also puzzles me. I'm sorry if I'm talking all the time about things that puzzle me, but there are so fundamental questions for which you don't find the answer that I think, how is this possible? For example, suppose that the random variables are not real valued, but they live on another space. They live on a torus. The observations are curves, maybe images. What should we do then? And just taking the very simple case of circular data, which is data living on a circle, the bivariate case. So you have two wind directions, θ1 and θ2. Wind direction, let's say at 4 o'clock in the morning, and a wind direction, let's say at 6 o'clock in the morning. These are the two random angles. And you want to somehow express dependence between that, or a dependent structure. And well, there is something which is called circular, which is like the copula version for circular data. There is a paper just appeared where you find some information on that. And essentially, I'm not going to repeat that again, but you have the joint distribution function of the two angles is coupled by this circular through, well, you have to properly somehow get to your transformed marginals. They are no longer uniform linear marginals, but they go back to a uniform circular density. Now, you might say, okay, then it's done. No, it's not done, because essentially you have to deal with, of course, this periodicity, which is there, which is not so easy. And so the question that you might raise here is, how do you measure dependencies here? And I think I probably have to stop here. So that's what I will do, but you will find some information, and you can look at this paper and you find some measures. But actually, we are only at the beginning of answering that question. In the bivariate case, circular data, I'm not talking about data on the torus. I mean, I'm a bit surprised about that, but maybe you don't share my surprise. I mean, that's also possible. Thank you very much.
Irène, for your nice talk. Now it's time of the discussions. The first one has been quoted by Irène during her talk, and is Professor Fabrizio Durante from the University of Salento.
Thanks, Irene, for a nice talk. I'm sure that everybody appreciates a lot. I prepared some comments about the talk that, as you have seen, was basically fundamental, in the sense that it touched a very fundamental issue about dependence. And what was clear from the talk, I just show you some comments about, let's say, the other side of the moon, is that the talk by Irene was focused on the measure of association, which is a kind of a broad term that includes many things, and then somehow they are called concordance. So it was very much interesting on essentially quantify how much large value of one variable are associated with large value of the other, or small value of one variable are associated with small value of the others. But you should be aware, clearly, but you know already, that there is also the other issue of the measure of dependence, when you want basically to quantify the issue of predictability from one variable, that from one outcome X to another outcome Y. Mathematically, the two measures are quite different, and it actually is not exactly the same issue clearly. In particular, while association measures are usually bounded, or better, can take negative value, the negative association, dependence measures are between 0 and 1. About the fact that association measure can take negative value, there is a whole literature at the moment about what is the upper and the lower bound for association measure. And this you can see, for instance, in the previous talk, all the possible constants have been formally and theoretically justified as the correct upper and lower bound, but there is still some open problem there. So we know that clearly in this case we have perfect dependence but no association, for the simple fact that the small value of x corresponds to large value of y, or you may have both cases. But so you may have two random values which are perfectly dependent and perfectly associated. Historically, the issue of looking at axiom for such a measures started in the field of dependence measures, as say Irène, in the 50s by Irène. Here I just copied just to give an idea what was also the, let's say, language at the time in order to look at these measures. In the very recently, the field of, again, this dependence measures, so they are bounded from zero to 1, they are included from 0 to 1. There have been a lot of measures that are popular here. In particular, the distance correlation by Zelecki and co-author, the mutual information coefficient, which appeared in a paper by Sciences, was almost immediately, let's say, named as the new correlation from the 21st century. Or in the really last year, some paper about the so-called Chatterjee measure of dependence. So there is many things ongoing on there. And in particular, from this field of dependence, you can also see some questions that apply as well to association measure, and that I would like to ask Irène about. In a recent non-technical paper in Bernoulli News, Fangan put a number of desirable statistical property about the measure of dependence. In particular, the first one is simply, and this property are related to the fact that usually you are using association or dependence measuring exactly to test independence. Now, the first property is just a call for the use in such a test of distribution-free measure, but for association measure, there is no problem. It just depends on the copula, no aspect of the marginal. The other three properties that are somehow more fundamental, again, as a word. In particular, the issue of consistency. For most, I would say almost all of these association measures, under independence, the measure is 0, but the other way around is almost never true. Okay? So the issue is whether anyway, you can have the opposite of this implication for some large family of distribution XY under some specific measure of association. So the issue is in which sense you may try to generalize this to if and only if condition, measure 0 if and only if independence. Another problem that we have noticed, especially for dependence measure, and there is a long discussion many archive papers recently about the Chatterjee measure, is to measure the power of such an independence test. In particular, basically the question is about the power for some, let's say, for smooth parametric model. So try to see whether you can really detect independence against dependence. And finally, there is a clear problem that at the increase of dependence become even more necessary to solve is the issue of computational efficiency. So basically, to B, C, and D, they apply, this comment applies as well to measure of association. My question is whether Irène could suggest us some indication to work on this aspect, on this aspect. Then I come back to the axioms that I like very much because it shows the mathematical soundness of all the procedures. And in particular, For me, it's very important to make clear the A8 axioms by Irène. So what happens if you add an independent component to your vector? How the measure should change? Okay, we have the similar axioms when you are doing also with comonotone component. You have a vector, you add a component which is basically a copy of a component that you already have. What happens to the association measure? Now it seems obvious that if you add a comonotone component, you are adding dependence to the whole vector. So in general, you should increase the association measure. The problem is that in general, this property is not easy peasy because you have many cases when it fails in practice. And this is a case of some Spearman's extension, some Gini's gamma extension, and so on, as was shown both in the case of association measure and in the case of dissimilarity measure that you apply. Another interesting axioms that you may formulate was exactly not in the talk, but in the previous paper by Irène, was about this. Suppose that you add one variable to a vector. Now it is natural that what you would like to have for an association measure is that the new measure is somehow bounded by the previous information. So it should be somehow bounded by the information of the domain of the association measure in dimension D plus some other information that could be the increase of the dimension, for instance, or some property of the copula. I don't know. Perhaps Irene knows now. This question is quite fundamental because it applies exactly to the issue of variable clustering, that we have seen. And under clustering, under hierarchical clustering, this is called, you can translate in terms of reducibility. As we know, in hierarchical clustering, you start from the bottom to the top and start to put together, for instance, the pair of variables which are mostly dependent or mostly correlated. It is clear that when you want to go to the high-level hierarchies, you put another variable, and the global dependence should somehow be lower because we have already clustered few of them. So in this case, it is natural that a natural requirement would be that under some condition, like this one, so if you have found the most dependent couple, then if you add any other random variable, your dependence should be smaller. Now think at this in the context of positive dependence, when you want to cluster just variables which are positive dependence. This immediately poses the question of what happens in the limit. When you add variables to your clustering procedure, and somehow you want to have some kind of, I'm not technical here, monotone convergence of the sequence of association measures. Clearly, it is difficult to find a natural example when, let's say, you may really obtain this monotone convergence sequence. And the question is whether there are some idea about this. Finally, a couple of comments about estimation. The first one is this. It was written on the slide that basically the quality of the estimator of the association method depends on the quality of the performance of the empirical copula process. Now, there have been various smooth versions of this empirical copula process that goes under different names, beta copula, Bernstein copula, checkerboard copulas, and so on. The question is whether in the estimation of Kn, they really provide some improvements. But as far as I know, it's not so obvious at the moment. And another question, which is a bit more general, perhaps is this. When estimating tail dependence, basically you are estimating some limiting behavior. I was also always tempted to put some parametric or semi-parametric assumption there, especially if you work with not so many data. But anyway, Irène presents something about the non-parametric issue and the non-parametric estimation. So my question is whether she would suggest some, let's say, empirical rule of thumb in order to give some practical advice when we should really on non-parametric estimation in the estimation of the tail dependence coefficient or when instead perhaps as slightly, let's say, a not so strong assumption like the extreme value assumption could be enough. That's my question, but thanks again, Irène, for the talk and for all your work on the field of dependence.
Okay. Okay, thanks to Irene for nice presentation. And I'm not an expert in these topics, and so I've learned a lot by reading your papers and also by reading your slides. And in this discussion, I have the intention not to make comments like Fabrizio, but to analyze and to propose some suggestions and ideas which could be useful in a different approach. The approach based on the notion of divergence. And on these comments, I would like to know your opinion. So the main topic, as we have seen, is to measure the dependence when we consider a d-dimensional random vector with d greater than 2. And instead of considering an approach based on copulas, the idea is to follow an alternative approach based on a suitable notion of divergence. The basic idea is very simple, because the aim is to measure dependence by considering a sort of distance between the estimated joint distribution and the estimated joint distribution in case of independence. So if we consider a continuous random vector capital X, and we focus in particular on density functions. So there is an unknown density function related to this vector. We have the marginal densities, and then we can specify the joint density in case of independence. So the aim is to specify a suitable measure of specified in this way as the divergence between the quantity called f hat and the quantity called f0 hat, which correspond to the estimates of the f and the f0 joint density using the observed data. F0 is the joint density in case of independence. With regard to this approach, there are some difficulties. The first is that clearly we do not know the true data generating model, and so the true f is unknown, but it's also difficult to specify a useful statistical model to describe the observed data, because we may have a complex data structure, and also we have to deal with complex dependencies. So an approach alternative to copulas could be to specify a sort of surrogate for the true f by means of a sort of model combination. So we may consider a set of simple basic density function, d-dimensional density function, Pj, and with the aim of combining them in order to get this sort of surrogate for the true f. One way to combine these component densities is by means of this kind of multiplicative model combination. This is one possibility. It has some advantages that I have no time to discuss here, but this is one of the possibilities. In this case, we have to compute the normalizing constant, and this is not easy, general. And we have to deal with the vector W, which is the vector of non-negative weights, and also with the vector theta corresponding to the vector, including all the unknown model parameters. The second difficulty is related to the fact that we have to estimate this surrogate model. and this could not be easy. In particular, when we consider the multiplicative combination, we have to compute the normalizing constant, and this would be challenging. And then we have to consider the fact that the dimension of the vector of the unknown parameters could be very large. To face this problem, one idea is, for example, to consider a set of inferential procedures different from the usual ones. For example, we may move from the classical log scoring rule to an alternative scoring rule. For example, the Hiva-Riemann score does not require the computation of the normalizing constant, which is given here. Moreover, in order to deal with the fact that we have a large dimensional parameter vector, one possibility is to specify suitable boosting type algorithms in order to specify an optimization procedure useful in this multidimensional setting, which also perform a sort of regularization. The third point is an important point. I will not discuss this point, but it's very important because we have to think about the choice of the divergence. We may consider the general class of field divergences, but we also know that each different divergence measures some different aspect of the densities taken into account. Here we have, moving to the conclusion, a very simple example within the Gaussian world. And if we consider a d-dimensional Gaussian vector capital X with a null mean vector and a covariance matrix given by capital sigma, and the aim is to estimate sigma and to compare this matrix with the estimate of sigma 0, which is a diagonal matrix specifying the independence situation. We may have problems in the estimation of the matrix sigma, in particular when the dimension is quite large. And this is necessary in order to specify an association measure like the KL divergence given here. So one solution could be this one. We may move from the covariance matrix to the precision matrix, which is the inverse of the sigma matrix. And if we consider this matrix, we have an idea about the conditional dependent structure related to this vector, which is quite useful when we consider Gaussian Markov random fields, for example. And we may also consider this very simple and interesting fact related to the result that say that when we combine d-dimensional Gaussian densities and with the aim of specifying a sort of surrogate model for the original X, and when we consider these component models having a specific precision matrix Qj, what we get at the end is again a Gaussian distribution with a precision matrix, which is the linear combination of the components one. The crucial point now is to specify a suitable system of component matrices. And here we have some possibilities. This is a very simple one. If we assume that the true Q has a sort of band structure, so there is a sort of R-type dependence, we may combine component precision matrices of this kind. If we don't have an idea, a real idea about the form of the original precision matrix, we may combine these very general component precision matrices, which are a sort of pairwise precision matrices. It's a very general setting, and we may use when we do not have a precise idea about the dependent structure. Here we have a very simple application to a real data set, and here we can see with this heat map the estimate of the unknown precision matrix using this very general combination of components we consider an inferential procedure based on the invariance score combined with a suitable boosting algorithm. From this estimate, we may compute, for example, one or different association measures based on a particular notion of divergence. So these are simple ideas related to an approach which is very interesting. But as you told in your presentation, this is an approach which needs a lot of additional work. Okay, thanks.
Thank you, Paolo, for your interesting discussion. So before moving to the reply, there is a question from the audience. Okay.
You mentioned in passing the mutual information, and this was brought up also, which is would be the as a divergence measure as well. Now, when you look at work done in this area, mostly the associated density are estimated by nearest neighbor methods or so forth. But there is a connection with copulas because essentially you need to estimate the expected log copula. Is there any work done in this area? Have you considered this in your work? Thank you.
Yeah, yeah, in fact, that's
Can answer to all the questions at the end.
I can answer all the questions, but maybe I'll start with this one because the other ones I wrote down. Yeah, okay. So essentially, yes, we basically are using kernel estimation for the copulas when we are dealing with these phi divergences. And maybe I can right away answer one of the questions. I will not try to answer all of them because that will be a bit too much. But I will try to answer questions of Fabrizio together with those from Paola, and I go back to that list of HAM 2021. And actually, the answers to B, C, and D are like, yeah, they're open questions, I think, mainly. The answer to B is something I think I know some kind of answer to, in the sense that when you look at phi divergences, and you look at phi divergence, there is a function phi that you need to choose. So if you take phi like phi of t, the t times the logarithm of t, you end up with mutual information. If you take phi, the square root of t minus 1 squared, you have the Hellinger distance. If you take phi of t, the absolute value of t minus 1, you get what is called robust copula divergence. The nice thing about these phi divergences is that we could show actually that you have this equivalence, your HAM number B, I think, basically when this phi is like strict convex. So it rules out the robust copula measure, but it allows like mutual information and the Hellinger distance. So that's actually quite nice. So that's a theorem that we showed that if you have that the phi is like strictly convex, you get this equivalence, which we were very happy about. For the computational things, as I said during my presentation, for the phi divergences, we are able, and that actually links up with your question about the correlation matrix, when you have like elliptical distributions and even meta-elliptical distributions, there is the correlation matrix that comes in. And we started calculating these phi divergences under this very general setting, right? So it goes beyond normal models or even normal copulas. And essentially what we noticed is that, again, something very surprising, that if you look at mutual information, you get an expression, an explicit expression, which we were very happy about, which is purely in terms of the correlation of everybody together divided by the product of the correlation matrices. So very natural. If you go to the Hellinger distance, so you take another phi function, we found for this case of the meta-elliptical distributions, right, or copulas, whoever you want to call it, something which is a function of R and the inverses. So there the precision matrix comes up. Now, if you then think of in terms of estimation, I would go for mutual information. And another thing you mentioned, which is extremely important, is the dimension. There I will do actually penalization, to be honest, for forcing the matrix to be sparse. That's something we are doing right now, but and I have no idea how it would work out, but that's obviously something that one should do, right? Let me try to answer some more questions if I can. Yeah, you're absolutely right for the semi-parametric. I think both of you asked that question about semi-parametric model. Actually, in the context of the phi divergence, when the dimensions really grow, we basically do that. We start working non-parametric up to a certain point in this variable clustering. And then when the dimensions really get too high, we basically switch to a kind of semi-parametric modeling. And because that's what is workable for the moment. But indeed, there is, I think, you know, there are so many questions that and all of the questions basically are like extremely important question. I mean, take the 4 points of Hum. I don't know. Optimal transport ideas, if you go back to doing that message, that for normal, very interesting things you find. You use the Wasserstein metric and you basically find, in some sense, in a normal case, you find like the eigenvalues of R are coming up. Very natural, but going beyond that, we were not able to do for the moment. Would be very interesting to basically try to get to that point, but we are not so successful for the moment. But for a normal case, you basically can reduce it back to the eigenvalues actually of your correlation matrix, essentially. I'm not sure I answered all the questions, but I think also
There's
time
another
is
question
running.
fast from the audience.
Okay, so thank you, first of all, for this very clear presentation. I'm a physicist, so undoubtedly I will manage to embarrass myself if I ask a question, but nevertheless, as a particle physicist, I'm interested in the tail of our distribution because there's where new physics hides. So we are keen to studying their multidimensional properties, of course, but I fail to understand how copulas play there, because while copulas are handy as they contain all the multivariate structure of the data, they do not, my understanding is that they do not retain the information on how much extreme these events are as they wash out the variance of the marginals. So can you educate me on what is that we gain by studying them with copulas?
Yeah, actually, the key point for copulas is essentially that they really are like, when you have a joint distribution, right? There is a dependence in there, and there is the marginal behavior. Well, the copula in some sense is that concept that purely governs the dependent structure, and it's independent of the marginals. So I can show you, like in a two-dimensional case, I take the same marginals and I take a different copula, and your scatter plot looks very different.
No, but how much extreme their events are is lost when it's the copula.
No, because you can work with extreme value copulas, which is like a class of copulas that essentially is designed for that. Yeah, so you basically could work with that, but of course you need to know that this is like modeling, right? I mean, you are making an assumption there.
Thank you, Irène. Thank you, Irène, for accepting our invitation and also for your nice speech. Thank you also to the discussion by the two discussants. Now